There's this common misconception in tech that going back to basics means things get easier.
Right.
You think, I'm just revisiting the fundamentals. This will be a breeze. But in computer science, and specifically for this course, CS330, programming languages and compilers, basics feels a lot more like, unforgiving.
It is. It's the difference between driving a modern car with all the assists versus, trying to fly a World War I biplane with no instruments.
Exactly.
And we're looking at Lab 1C Introduction for the spring 2026 semester. The title sounds so simple, but the reality is much sharper.
Right. And reading through these lab notes and also the syllabus from the instructor, Dave Reed, I get the sense that this isn't really about learning C syntax.
No.
I mean, frankly, most of the students taking this course probably know how to write a loop or an if statement. This feels like it's about something else entirely. It feels like calibration.
That is the perfect word for it, calibration, because look at the end game. The syllabus makes it really clear. The goal of this course is to build a compiler.
Right.
A huge project.
A huge project. You're constructing a machine that translates language. And to do that, you can't just be a coder who sort of hacks things together until they work. You have to be an engineer who understands the molecular structure of the tools.
So Lab 1 is effectively boot camp.
It's a boot camp for precision. Yeah.
In that precision, it starts before you even write a single line of code. It starts with bureaucracy. And I really want to spend some time unpacking the law and order aspect of this lab, the file naming, the directory structures, because usually I would gloss over this stuff, but the penalties here are steep.
They're binary. It works or it fails. There is no partial credit for almost getting the file name right in a compiler build system.
Okay, so let's look at the file naming conventions first. The notes are incredibly specific. If you're doing a team problem, the file has to be lab1prod-t-tag.c.
Yep.
And if it's individual, it's lab1prob-tag.c. Note the hyphens, note the T, but here's the part that actually stopped me in my tracks.
Oh, the text-based answers. The text-based answers, exactly. There are questions asking for explanations, conceptual stuff, not code. But the instructions explicitly state, place the text answer inside a .c file, and then they just casually add, and I'm quoting here, it won't compile, which is fine.
It sounds like a paradox, doesn't it?
It sounds wrong. Why would you intentionally put garbage text into a source code file? I mean, usually the compiler screaming at you is a bad thing. Why is Dave Reed asking students to break the build on purpose?
Well, think about it from an artifact management perspective.
Okay.
In a typical dev environment, if you have 30 teams submitting work, and half of them submit PDFs, some submit Word docs, and some write the answer in an email or a AME file, you have chaos.
Right. Administrative chaos. Things get lost.
Exactly. By forcing the text into a .c file, even if it breaks the build, you are standardizing the container.
So it's about treating documentation as code.
Precisely. It keeps you, the student, in your IDE, the integrated development environment. You don't context switch to a word processor. You stay in the terminal. You stay in the editor.
And it reinforces the idea that everything you deliver is part of the package.
Everything. Even your explanation is a code artifact. It forces you to treat your words with the same file naming rigor as your functions.
That makes a lot of sense, though it still feels like scratching a chalkboard to me, leaving that uncompilable text in there.
I get it.
Now, speaking of staying in the terminal, the directory structure, we've got CS330 team lab work and CS330 individual lab work. This isn't just about being neat, is it?
No, not at all. This is functionally required by Git. If you're in the wrong folder, your version control history is going to be a disaster.
The Git workflow in this lab it's intense. I mean, it is scripted down to the keystroke, and it's strictly a team exercise.
It has to be. Version control is the heartbeat of collaborative engineering. You cannot build a compiler solo in a vacuum. And the lab describes a very specific dance for the team submissions. It distinguishes between the host student, the one driving the keyboard, and the other students.
Let's walk through that host workflow because there's a specific command that I know catches people out all the time. Git add.
The trailing dot.
Trailing dot, right. Git add space dot. I've seen junior devs miss this constantly. They type git add, hit enter, and Git just stares back at them.
Well, the dot is a wild card. It means everything in this current directory. If you just type git add, nothing happens because you haven't told Git what to stage.
So this lab is forcing you to be intentional about it?
Exactly. You're telling the system, look at everything I just changed here. Then you commit with OAM and a message, and finally git push.
Okay, so that pushes the code up to the repository. But here's the friction point. I'm the host. I've pushed the code. My teammate sitting next to me can't just start typing on their machine, right?
If they do, they will create a merge conflict instantly. The other students have to run git pull. It's like a relay race. I pass the baton, that's the push, and you grab the baton, the pull.
If you try to run without the baton, you crash.
You crash.
There's one more step here that feels like a final boss mechanic for the submission. The tag.
The annotated tag, yes.
The command is git tag, a lab 1 submission, 1 meter lab completed. And then, and this is the real kicker git push follow tags.
That follow tags flag is so critical. A lot of people think git push just sends everything. It doesn't.
It just sends the commits.
It just sends the commits. Tags are metadata pointing to commits. They're like sticky notes on a file cabinet. If you move the cabinet, the code, but leave the sticky note on your desk, well, the person receiving the cabinet doesn't see the note.
So the instructor looks at the repo, sees the code, but doesn't see that submission tag.
Correct. And technically, that means you haven't submitted. I mean, in the industry, this is how release management works. You don't just say, use the latest code. You say, use version 1.0. That tag is the product.
So this lab is simulating a production release cycle.
Exactly. If you don't tag it, you haven't shipped it.
High stakes for a Hello World assignment.
Hey, Ray.
Okay, let's shift to the actual C problems. We have a mix of team and individual work. The team section starts with assigning roles. Chief understanding leader, chief equity leader, chief note taker.
You know, I really appreciate that chief understanding leader role. It sounds a little funny, but it creates a formal check against passenger syndrome.
Oh yeah, where one person codes and everyone else is just watching TikTok.
Right. This role's entire job is to verify that everyone gets it before the team moves on.
So the team is set up. They dive into problem T1, escape characters, N for new line, T for tab. Standard stuff. But then there's
the bell.
Why do we still have a bell character in 2026?
It's history. It's heritage. In the days of physical teletypes, printers were loud. If the system crashed, printing an error message might not be enough. You needed to physically wake up the operator.
The machine would literally ring a bell.
It would ring a bell. Today, A, which stands for alert, might trigger a system beep or a screen flash, depending on your terminal.
So it's a reminder that print isn't just putting pixels on a screen, it's sending signals to a terminal.
Exactly. And backspace, it's similar. It moves the cursor back one slot. It doesn't actually delete the character by default. It just rewinds the position. It turns the output stream into a control stream.
Which leads perfectly into the formatting challenges and problems T2 and T3. Temperature conversion, Celsius to Fahrenheit. The math is, elementary school stuff. But the requirement is to add a column header.
Add a header. It sounds so trivial. In Python or Excel, it's just done for you. In C, you are manually managing every single space.
You literally have to count the spaces.
You do. You have to align the C in Celsius with the numbers below it, using tabs or spaces. It teaches you that formatting is just another form of data computation. There's no magic layout engine. You are the layout engine.
And speaking of being the engine, let's talk about problem T4. The histogram.
Yes.
The team has to print a visual representation of how often digits appear in the input.
This is such a classic challenge. It combines data structure management with visual logic. You probably need an array to hold the count slot 0 for the count of zeros and so on.
Right.
But then, to print this histogram, those bars of asterisks, you have to loop through that array and print a character n times.
It's data visualization at the absolute lowest level.
It is. You're not calling some fancy plot function. You are iterating through memory and deciding character by character what to display.
Okay, now I want to spend a moment on T5. This feels like the heavy hitter of the team section. Demonstrate that function parameters are passed by value. This is a concept that trips up so many people coming from higher level languages.
It's the fundamental divide in programming languages. Pass by value versus pass by reference.
Okay, so explain it for us. What does C do?
All right. Imagine you have a document, a contract, and you want me to edit it. In a pass by reference language, you give me the actual physical contract. If I cross something out, it is crossed out for you too. We're holding the same piece of paper.
Right. We share the same object.
In C, pass by value means you don't give me the contract, you photocopy it. You hand me the photocopy.
So if you burn the photocopy,
the original in your hand is perfectly safe. C creates a clone of the variable when you pass it into a function. The function operates on the clone. The original memory address is untouched.
So for this assignment, the students have to actually prove that this happens.
Yes. They'll likely have to write a function that tries to change a variable, say, takes x, which equals 0, and tries to make it 1 inside the function, and then print x back in the main program to show it's still 0.
Why is C so strict about this? It seems more efficient to just share the paper than to photocopy it every time.
It can be more efficient, but C defaults to safety and isolation. It prevents side effects, where some subroutine accidentally corrupts the main program state. Of course, C can pass by reference, but you have to do it explicitly with pointers.
Which we haven't gotten to yet in Lab 1?
Not yet. This lab is establishing the default behavior, isolation.
That is a key insight for later when they build their compiler. They have to decide how their language handles memory.
Exactly. They aren't just learning a rule, they're learning a design choice.
Let's move to the individual assignments. This is where the safety net is gone. And frankly, problem I1 is my favorite pedagogical trick I've seen in a while.
The learning by failing exercise.
Yes. Leave out parts of the Hello World program and collect error messages.
It's brilliant. Usually, students fear the red text. They see syntax error and they panic. This assignment forces you to invite the error.
It's exposure therapy for coders.
It is, but it's also linguistic training. Compiler error messages are a dialect. They're terse, often confusing. By intentionally removing a semicolon and seeing expected before token, you build a mental map.
You learn that missing brace might actually show up as an error 3 lines down.
You are reverse engineering the compiler's logic by breaking it. You're learning to read the symptoms so you can diagnose the disease later.
Because when you build your own compiler, you'll be the one writing those messages.
You need to know how they work.
Yep. Then we have I2. Prove that relational operators result in values 0 and 1. This goes back to the basics of truth in C.
Or the lack of truth, really. In modern languages, you have true and false, Booleans. In standard C89, the old school stuff, there's no Boolean type.
They're just integers.
Right. 0 is false.
Yeah.
Everything else is true. But specifically, the operators themselves return 1 for true.
So if I ask the computer, is 5 greater than 3, it doesn't say yes, it says 1.
And if you ask, is 5 less than 3, it says 0. The assignment asks you to print these results. It strips away the abstraction of logic and reveals that at the bottom, it's all just arithmetic.
It's a very Matrix moment. It's all just numbers. Speaking of which, I3. Printing the value of EOF.
End of file.
We think of the end of something as a state, a void. But C assigns it a value.
It has to. If you're reading a stream of data, byte, 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 how do you know when to stop? You need a sentinel, a flag.
And that flag is EOF.
Which is usually defined as match 1. This problem forces you to print that value. It makes it concrete that the end is just another signal from the system. It isn't magic. It's a specific integer that your loop has to wait for.
And if you don't check for it, your loop runs forever.
Forever.
And finally, I4, recursion. Creating a power function like 2 cubed, but using recursion instead of a loop.
This is the bridge. This is the bridge to the rest of the semester.
Why? I mean, we established loops are efficient. Why force recursion for simple math?
Because you cannot build a compiler without recursion.
That's a bold statement.
It's the reality of the data structures. Code is represented as a tree, an abstract syntax tree. You have expressions inside functions. A tree is a recursive structure. To walk down a tree, you need a function that calls itself.
So if you can't write a recursive power function now,
you will have 0 chance of writing a code generator for a compiler later. This isn't a math drill. It's a structural drill. It's forcing you to think non-linearly.
We've covered the code, but we have to address the bit buddy in the room, the AI policy.
It's 2026. You can't ignore it.
Yeah.
And the syllabus and lab notes are very specific here.
Dave Reed has this framework of 3 modes. Mode 1, I've got this. Mode 2, vibe coding. Mode 3, you do it.
I've got this is 0 AI. Vibe coding is AI assistance, where you modify the output, you're the editor, and you do it is full generation.
Now, what I find really interesting is the restriction for this lab, for Lab 1. You can't just generate the whole thing.
Right. The requirement is that at least 2 exercises must be done in I've got this mode, 0 AI.
Why insist on that? Why not just vibe code everything?
Because of what we just discussed. Because of EOF and memory addresses. If you don't understand why C passes by value, or why a format string needs a specific escape code, you cannot effectively prompt an AI. You can't debug the AI when it hallucinates.
You have to earn the right to automate.
Exactly. I've got this mode as the foundation. If you skip that, you're just a passenger in the car. And the goal here is to build the engine. You can't ask an AI to build me a compiler if you don't know what a compiler is supposed to do.
And you have to document it all in the RehabMD, which LLM you used, which mode.
Transparency. It turns the use of AI from cheating into tool selection. It's a professional engineering standard.
So pulling this all together, Lab 1 is a lot more than just C introduction. It's about establishing a worldview.
It is. It's saying precision matters. Protocol matters. The difference between a working submission and a failure is a single Git tag or a misplaced file. It's moving you from I code for fun to I engineer systems.
It's the difference between playing with Legos and pouring concrete foundations.
That is it. And once that foundation is set, once you stop fighting Git and start trusting your directory structure, then you can actually handle the complexity of building a compiler.
I want to leave our listener with a thought on that EOF concept we touched on.
Sure.
We usually think of nothingness or the end as the absence of data, but in C, as we learned, EOF is a value, a defined integer. It suggests that for a computer to understand nothing, we have to turn nothing into something.
That is a profound way to put it. The system can't comprehend a void. It needs a definition for the void.
So if the end is just a number, maybe we shouldn't be so afraid of it. It's just one more data point to process.
Just make sure your loop handles it correctly or you'll run forever.
Words to live by. Get your tags right, check your error messages, and welcome to the compiler track. Thanks for diving in with us.
Happy coding.